The Global Sanitation Graduate School is the world's largest platform for capacity building in citywide inclusive sanitation. We offer educational programs in sanitation with a focus on participants from low and middle income countries. We are expanding rapidly and welcome new members. Interested? Contact us today. www.sanitationeducation.org.
Good morning. Good morning to our viewers all over the world, from the Netherlands, from Delft, from IEG Delft. And my name is Damir Barjanovic. Here in our studio, in our room, we have Tina Velkushanova and Mariska Ronteltap. And from Thailand, we have Tamarat Kotatep. And of course, there is a fifth member of our team, Linda Strande, and she will join us with a video. So this is a fourth edition of Global Sanitation Graduate School Keynote Series. This is a monthly event where each of our partners in Global Sanitation Graduate School will present each month a topic of their choice with two people, experts in the field. And the first keynote was here from Delft on innovations in wastewater treatment. The second one was from Meru University on practical applications of sanitation solutions. The third one was from AIT on innovations in non-sewered sanitation. And this is the fourth one. The topic of today is about the methods for fecal sludge analysis. This topic is a hot topic, and it's what we will present today is the part of the activity of the global partnership for laboratories for fecal sludge analysis. This partnership at this moment has 11 or 12 laboratories in Europe, but also in Africa, Asia, and Americas. And this is a part of the promotion of the laboratory work within a citywide inclusive sanitation. Today, we will talk about our new book that it's just on the market and will be officially launched in Denmark this year in September. But we will also talk about the content of the book. Tina will tell a little bit about that more in details. And we will talk about the role of laboratories in our business in citywide inclusive sanitation. So that will be the topic of today. After that, after the presentations, we will have a hopefully vivid discussion. So I would like to take more of the time that we have available. And Mariska volunteered to be our moderator of today. And so, Mariska, floor is yours.
Yes, good morning, everyone. Very nice to be here and to talk about this nice topic with all of us. So what the plan is for today is to talk really about the chapters of the book and give you some inside information. And of course, you have already downloaded the book and read it in detail. And if not, go and do this straight after, because it's all freely available. And really, we all hope that you make very good use of this and also use it in your own communities. So we'd like to start with Tina giving a short overview of the chapters and talk a bit more in detail about her specific topic.
Thank you, Mariska. Good morning, everyone. It's really great to have our special edition of the Keynote series. And I'm just going to go through the overview of the book and some of the chapters. So firstly, just to mention some of the things that Damir maybe already mentioned, the book was published only last year. It took some time to compile everything. The book is open access, so the electronic version is completely free to download from anywhere. We have high resolution, low resolution, so it's suitable for downloads from any part of the world. The book consolidates decades of knowledge on methods for sampling and analysis of fecal sludge. The target audience is suited for any kind of professionals in the field of non-sewered sanitation, fecal sludge management, and sanitation in overall. Also very suitable for laboratory personnel, researchers, students, or technological developers in the field. The book was peer-reviewed, and we had a great contribution from over 50 or 60 authors, contributors, and reviewers. So each chapter was peer-reviewed to make sure that the quality stands out and it's understandable to the wider audience. And this book was a collaborative effort and in partnership between 4 organizations. All the editors were representing the IHE Delft, EWAG, UKZN, the WASH R&D Center, and the AI team. Also, we had quite a good partnership with the Partnership for Laboratories of Fecal Sludge Analysis, the Global Sanitation Graduate School, and the Swiss Agency for Development and Cooperation. We also, this project was funded kindly by the Bill and Melinda Gates Foundation. Okay, I need to direct. No. Apologize.
The arrows.
It's always the case.
If you just talk without the next slide. Okay.
Okay, I'll speak without the next slide. So we have 8 chapters of the book, which were representing different parts of the. Now everything was removed. Okay.
The PowerPoint again on the bottom. It doesn't work. The mouse is for your computer and not for this.
Yeah. Okay. I'll try once again. Apologize for that. Share.
Remarkable.
Okay, so I think you just continue.
Yeah. Okay. The book has a number of chapters. We have 8 chapters in the book, which have been developed by different authors and contributors, and we had different reviewers for each of the book chapters. So the first one is the introduction or the setting of the stage. The second chapter is on the characterization of fecal sludge, which has been which I'm going to speak a little bit more. Then we have the sampling methods, which Tamarat is going to touch a little bit on. Then we have the experimental methods for from laboratory analysis, how to scale up to larger scale. Then we have the quantities and qualities of fecal sludge, which is Linda has prepared her nice overview. Then we have the modeling chapter of Damir that he's going to present. We have a chapter dedicated on simulants of fecal sludge. And then we have also a chapter which is the largest one, which is dedicated on the different methods for fecal sludge analysis. With this, I wanted us to move to the next part, which is the chapter 2, and we're still trying to find out how to switch to the next one.
So which one do you want now, Tina?
No, it's in the same presentation.
I'm not Tina.
The problem is how to move to the next slide in that presentation.
You have some technical problem with the moving slides around?
Which early on was working fine.
I can get the chat on the screen. I can see if there's already a question that we can do in the meantime.
Okay, I'm just going to do this.
Perfect.
Yes. As I said, these are the different chapters. Let's see. No, it's not going to work. Then we move to them. And then we have the chapter on fecal sludge properties and consideration for characterization. Myself and Linda were the authors of this chapter, and then the objectives were to present 4 types of fecal sludge depending on the total solids content, provide a brief overview of the factors that influence characteristics of fecal sludge along the service chain, explain the relevance of selecting different fecal sludge properties based on the objectives of characterization, explain factors for consideration when selecting characterization methods, and provide guidelines for setting fecal sludge laboratories along the case studies of existing implementations. So when we speak about fecal sludge, we managed to distinguish 4 different types of fecal sludge depending on their total solids content. Why? Well, when we speak about the selection of the different analyses and the preparation of the samples, we need to consider that the different samples will have different preparation techniques, and also the different samples will have different characteristics that may vary significantly. So the liquid fecal sludge is with total solids of over 5%, slurry, which is between 5 and 15, semi-solid fecal sludge between 15 to 25, and solid fecal sludge, which is with total solids of over 25%. We already discussed also some factors that are influencing the characteristics of the fecal sludge along the entire sanitation service chain. For example, we can have the inputs that are going into the on-site sanitation that are influencing what would be the characteristics or the composition of the fecal sludge that is accumulated in the on-site sanitation over time. We have excreta, anal cleansing, water, or the different miscellaneous that could be solid waste, additives, or other cover materials. Along with this, we have other factors that are influencing the characteristics, which is the type of containment, for example, whether it's a dry or flushing system, the demographics, how many users use these systems, what is the frequency of use, whether it's in a rural, peri-urban, or urban setting. And of course, we have environmental factors, which could be the climate, temperature, groundwater, topography, or any other related environmental factors. So this results in a high variability of the fecal sludge. And in these graphs, we just show an example, which is from Durban, in South Africa, where through the UKZN, we have been working in the collection of different samples from different types of on-site sanitation systems. So you can see that different colors represent different types of on-site sanitation systems. We have dry pit latrines, wet pit latrines, community ablution blocks, urine diversion toilets, school toilets, or unimproved pits. So what we see also, the variation represents not only the type of the on-site sanitation, but then also it represents the sampling points from different layers of the sludge that has been accumulated. So this gives you also the idea of how important it is to try to unify the methods that we are following to be able to characterize the fecal sludge, because it is a highly heterogeneous type of material, and we can't follow the same type of standards and methods that are established for a lot more homogeneous materials, such as wastewater, for example. We have provided the different steps of the process of selecting methods for characterization, which we need to start with identifying the data needs, the purpose and the objective of characterization, select the desired properties related to this purpose, the properties that we need to measure. Then from there, select the analytical methods that we can use, undertake analysis, and analyze the data that has been generated. In this book, we provided 3 main groups of properties for fecal sludge, which are chemical and physical-chemical properties, physical and biological properties. Also in the chapter 2, we have included the setting up of laboratories for fecal sludge analysis, focusing on some case studies from fecal sludge laboratories along the globe with different partners, and providing different elements of importance, which include the personnel, training, the availability of good facilities for that, the types of samples, the health and safety aspects, equipment, and reporting. And speaking about laboratories, I would quickly go through chapter 8, which is, as I mentioned, the largest chapter and includes all the different methods that we managed to summarize. You can see that there was a long list of authors and even longer list of contributors and reviewers. The objectives of this chapter was to provide methods for protecting health and safety during collection, handling, transportation, storage, and disposal of fecal sludge. Also to provide information required to adapt and develop standard methods for fecal sludge characterization, including quality assurance and quality control strategies, and selection of appropriate methods, and also to provide an overview of existing methods for fecal sludge analysis being used in partner laboratories. The content in this chapter includes different aspects. So I'm going to show you the methods that are included, but we also included the health and safety aspects, such as standard operating procedures, what kind of personal protective equipment we need to use, vaccinations, inoculations when working with fecal sludge in fecal sludge laboratories, clean and dirty working areas for preparation and the analysis, how to handle the fecal sludge. We also have the quality assurance and quality control section, where we speak about the chain of command and the importance of equipment maintenance and calibration, checking compliance, and seeing what is accuracy versus precision, for example. We also have certain aspects speaking about fecal sludge storage and preservation, how to dispose safely the sample and the chemicals after the analysis, and different sample preparation techniques before the analysis, depending on the type of fecal sludge. And for the methods, we have 49 methods currently included. They are distributed between the 3 different groups that I already shown. These methods are modified from standard methods from wastewater, water, and soil science. And the level of modification is indicated in each method with reference to the original method used. These methods are based on years of experience by the authors of the book and working with fecal sludge analysis in the relevant fecal sludge laboratories. And the intention is that we can continuously upgrade and include new methods in the next revisions of the book. So this is just to show you the different types of analysis, methods for analysis that are included. The larger part is for the chemical and physical-chemical properties. We have solids, chemical, COD, fat and fiber, nitrogen content, phosphorus, pH, and electrical conductivity, elemental analysis, color, turbidity, settlability, and dewaterability. And we also have some pathogens measurement. And just to end, I just wanted to say thank you to our sheet manager, Chris Buckley, who was a major contributor and dedicated his life to this field. So that's from me. Thank you. I would pass to,
Melinda. Thank you so much, Tina. I was really impressed that you could memorize all the chapters by heart. That shows true dedication. That's really fantastic. So I hope you now all had a nice overview of especially all the methods that are in there and which characteristics you can look for. You know now that in the back of the book, you can exactly look for the standard operating procedures for all of these characteristics. And with that, we move on to Tamarad with his nice presentation. So Tamarad, we really look forward to what you have to contribute from the AIT point of view.
Sure.
Are you able to share your screen?
Yeah, I hope so. Is that okay? You can see my screen?
yes, Tamarad, just 1 second.
Yes, perfect.
Yeah, can you see my screen? Okay. Hello? Can you hear me? Hello? Tina, can you hear me?
Tamarad, we can hear you and we can see you.
Okay, so just to confirm that, thank you, thank you. So let me share again.
Thank you.
Okay, let me start. Thank you, all the organizers to join this, to let me join this interesting keynote that I'd like to share one of the chapters in this fantastic book that we developed quite some years ago that finally we can launch last year. And then one of the chapters that my team and myself contribute to that is about the sample collections and handling of the fecal sludge. So I'd like to brief you a bit that how we think about the sample collection and handling. Of course, in the wastewater treatment system, in the water treatment system, or the collection of the environmental samples, there are a kind of a standard method to do that. And then I think it's not really much discussed yet in our professional society, talking about this kind of how to properly manage and collect the samples from the fecal sludge system. So I think the very first thing that before we start planning for this collection and sampling of the fecal sludge, I think the very first thing is that we need to define what are the objectives of our sampling programs, of our sampling campaigns. Whether you just like to do the qualities or quantity as well. So this is also very important that to design and then to plan forward that what are the important figures or the procedures that we should comply with, such as if we would like to understand the estimation of the production rates of the fecal sludge from the containment from the on-site system. How should we collect the samples? How can we understand the system? Or whether we like to planning the emptying service for communities, so that perhaps it may need to discuss and thinking about that. What are the collections, whether it is the manual or the trucks or other kind of collections equipment, so that we need to plan properly that whether we can sample the inlet, outlet, for example, from the trucks, and how we can ensure the mixing properties of those sludge in the containers. We would like to define on the performance of the treatment system, on the evaluation of the operational parameters or monitoring of the treatment or the reuse. So I think that also very important to define and clearly define your objective first before we get into the planning or the sampling program. But of course, similar to those water samples or the environmental sampling techniques, the grab samples can be also used for the fecal sludge as well. So as we know that the grab sample is the CAT sample or the individual sample, which can provide a snapshot. We say that it is a snapshot because our system, starting from the container to the collection system to the treatment plant, the characteristics could be vary, as discussed by Tina earlier, that it could be vary, and then we need to prepare in advance that how should we define, or if you just like to know only the snapshot or not, or just thinking about that, whether we would like to get the representative samples along the time, along the flow, so that we can properly design the sampling plan. So another possibility is that we can use a kind of sequence of the grab sample to monitor and conditions over time, especially on the treatment system, that we can use, that we can sterilize. Otherwise, sometimes we get a very high concentration, another time in the same day we get a really low concentration, so that is not really the good representative of samples. The other one that we would prefer or recommend that for those researchers or for those practitioners to do that is that, if possible, we should be able to conduct composite sampling programs that it can provide more representative, and then it can characterize over the piece of time. As we know very well that it's not the same as the wastewater treatment system, that we could have a continuous flow of the wastewater to the system, but our fecal sludge is not. It's a kind of intermittent feedings, and also that we are not pumping out the fecal sludge from the containers every day. It's not that constant at all. So that it means the things that if you would like to understand better, the composite sample would be the recommended practice. Then it could be depends on your convenience time. Of course, it would be good to have a few days or couple days to have the composite, but it takes time. It takes too much of effort. So that we have to think about in the real life, that in the practice, that how should we decide whether it is within few hours or few days, depending on the conditions in the local conditions. And then the aliquot of composite samples need to be well mixed and minimize the kind of the contamination during the process as well. That's also quite important, how we ensure the well mixed, especially if, for example, you notice from the photo that it is a tank. Then the tank, it could have a kind of a scum layer, the liquid layers, and also the sediment layers. So that how can we ensure that when you collect the sample, it could be mixed, well mixed as well. Otherwise, we will get only the scum part, or if we deep down into the middle of the depth, it could be only the supernatant or the liquid zones, which is not very high concentration. So this kind of thing that we have to plan in advance and think about that. What would happen in the reactors in the container or in the tank or in the treatment system that we collect. Then from the device, so we recommended certain device that we can overcome those kind of issues. For example, that the vacuum sampling device which we have developed, which simply use a vacuum tank, and then we can define the depth that we would like to get, especially for those reactor samples that we would like to get from the surface layer down to the sediment layers. But if you would like to understand whether it is the scum, whether it is the liquid parts or the sediment parts, so that this kind of a sampling device can do. But of course, you can think about what are the other equipments or devices that we can define on this vacuum would be something that we have been used, and then it can do and overcome several local issues. Then from the in situ, the on-site containment technologies. So the in situ sampling from the wet toilets, for example, that we can think about that how we can get the samples. As we know that the fecal sludge can be very concentrated or can be very diluted as well, depending on the structures, depending on the design or the operational functions of the system. If it is septic tank, if it is cesspit, cesspool, if it is well maintained, or they connect to the drain or connect to the soak pit, like that, where we should go, where we should get the sample. So this would be something that we need to think carefully, that okay, if you would like to get the treated supernatant from the septic tank, for example, then it could be rather simple that we can collect from the wet containments, like from this photo that we can simply do. But if it is higher than the 15% of the total solids, that means that we may get from the kind of that really long time without any emptying of the on-site system or the container at all, then the solid could be very thick. Then it is not easy at all to pump it out or not be able to collect by your buckets. So you may need to think carefully that how we can get the appropriate sample, that especially to avoid a certain contaminant as well from the other contaminants. Then this kind of in situ sampling, especially for the dye contaminants, could be done by using this kind of cone-shaped sampling device. That, but we need to check first that whether it is very high or very low concentration of the fecal sludge sample, so that it is another challenges that we need to check from at the site. It may not be possible. Hey, I just prepare only that vacuum pumps with the tank or using the cone shape. But if you should use that the cone shape sampling device, it may not be possible to get from the very diluted fecal sludge sample, for example. So this is kind of thing that will very much depend on the location, very much depend on the system that we would like to get the sample from. Then in addition to that, somehow many of those sampling, like you have seen in these photos, that it's not possible at all. That we said, well, we would like to know the sludge quality in this kind of public toilets that having very, very high contaminated with the other solid waste, like plastic bags or some other papers, that and then how can we get to that? So this could be something that we may need to check, that whether it is possible to do during the emptying services. So during the operation, we may not be able to use such kind of a device or equipment to use that. Then we may need to prepare in advance or ask the emptying service providers to come and then get it empties, and then we can collect the sample accordingly. So that would be something that a challenge, but depending on those kind of system setup in the system. Then at the treatment plant, I think it would be rather simple if we design properly for the treatment plant. that from inlet outlet to define the performance, to define the operational concerns, and then somehow it would be similar practice that we did for the wastewater, but be aware of only that how should we collect the appropriate sample, whether it is the sludge or the liquid or the sediments out of the treatment system. Then this kind of sample, of course, another question would be that what would be the appropriate size? Nowadays, we cannot standardize yet, but we would propose that, for example, the composite sample, it could be a mixture of that beginning, middle, and end with 10 liters and mix properly. And then with that, we can use each of them for different purposes, for physical, chemical parameters or microbial parameters with the preservation. So that would be the proposal that we propose in our chapters. But of course, through the several research in the futures that we have review and collect more, we can suggest and brainstorm later that whether it is appropriate numbers or not. But with our experience from the AIT and our partner institution, we propose is that could be the sample size that should be collected from the system. Then from the dumping side like this, of course, it could be very much vary because from the different trucks, different source, it could be from the one household or apartments or the public toilets. Then the components or the composition of each truck would be different. So that is another thing that we have to think carefully as well, that how can we ensure that we collect the proper composite sample. Of course, with this practice, it could be possible, but how can we get from different trucks so that before we decide the appropriate sample size, we may need to check that whether it has the same source of the fecal sludge to come to the dump site, to come to the treatment plants or not, and then we can decide properly. Of course, the other things that another chapter we talk more in detail, but during the sampling or during the collection of the sample, it is also very important to be aware of these health and safety issues, that protective equipment like the shoes, the mask, the glove would be very important. And also that from the sample point of view, we need to prepare kind of a storage and preservation, identify the samples, that what are they and which parameters you are interested in to the analysis. So this is an example that should we do, whether we provide a certain preservation agents into the samples or not, and then think that whether it is need for what kind of parameter analysis. And then after that, the storage and preservation also required, because somehow we cannot do right away the analysis, then we need to have storage. So we suggest that the sample should be maintained at about 3 degrees Celsius in the refrigerators with the constant temperatures. So it could be separated as well, that the sample could be the sample pending for testing or during testing or waiting for disposal or disposal. So somehow the disposal of the remaining samples also very important. We should not be the one from our labs to dispose untreated fecal sludge to the drain, which is not that good at all, and we need to prepare in advance. So this is an example that did we do in AIT labs, in our NAS lab, that we have to separate the shelf in the refrigerator. That this is the area for the sample that pending for testings, or the sample during testings, that it could be different. Then also with that, it should have also the records. So somehow that we need to record properly in the forms. Otherwise, we may not be able to trace back that what would be and how we can trace the records of the sample bottles, and also from which sample, from which area. That could be the things. And then, of course, in the ISO standard, there is requirements that you have to specify carefully that how should we manage the sample testing and analysis. Then in that, the storage and disposal also very important, that before you dispose, you may not be able to dispose just drain into the drainage. So that it would be not good at all. So somehow we have to collect the unused samples, sample before we dispose, because somehow we found out that there are some errors during your analysis. Then this kind of a sample may be repeat analysis again to ensure that you are not doing not the big mistakes. Otherwise, you may fail into that the report. Then this kind of thing that also very important to have the standardized disposal period that before we can dispose them. Then in our system in AAT in NASLab, we luckily having a kind of that conventional wetland system as a disposal site of our sample. But of course, we have to report as well that how did we do, how much of the sample, how many sample. Then we have to put the record according to the ISO 17025 standards to verify our workflow. And with that, just to share with you a bit of our labs that our NAS lab have in this year, we have certified parameters, 6 parameters that we can say that we are one of the very first lab in the region that can analyze up to the level of the sludge concentrations. Normally in other labs that provide a service in our country, in the regions, it would be in the range of that the water and wastewater concentrations. But because we would like to focus on the fecal sludge, then we enhance our range up to about 20,000 for solid sample. Then it could be the things that we can offer this kind of lab for the sludge analysis. And then our lab is not just only for analysis. We also would like to be the proficiency testing lab that we are in the process of ISO 17043 certification, which should be able to complete within this year. So what does it mean? The proficiency testing is that we will be the one that send the sample. If some labs from your university, from your organization interest to test, to prove yourself whether you are the excellence in that analysis or not, you can test your capabilities, your proficiencies in analysis of certain parameters, so that we are moving in this direction, that we can provide proficiency testing services in addition to the analysis that defines ISO standard as well. So with that, we also like to propose that we are developing this kind of guidance or manual or SOP. Of course, in our books, we have certain chapters on that, but this would be more practical guidance or manuals to suggest or to help the other to setting up the fecal sludge laboratory. That it is take time for us, for example. We take about that. We took about that more than 2 years to standardize, to train our resource persons, the technician, and many others, so that it would require somehow that that we can share our lesson learned with you, that you can faster the process if you wish to be ISO certified lab as well. So with that, thank you very much for your attention of these chapters. Thank you.
Thank you so much, Tamara. That was super interesting. It was really nice to see your overview and your years and years of experience put into a summary of guidelines. I think you also learned quite a bit with your huge team in setting up the findings, and to realize what you've learned and what you've accomplished in the last decades. So it's a nice summary of all your work, but also a nice celebration of it. And you have quite an impressive football team there present in your lab. That's really nice. There are already some questions for you online, but we move those to the end of the session. And the next step is now to look at the video of Linda Stranley, who unfortunately couldn't join live today, but she has summarized her findings in a nice video.
Hi, I am Linda Stranley. I am leading the research group MUSE, Management of Excreta, Wastewater, and Sludge in Department Sondek at AAVOG. I'm going to present here some key ideas behind the development of Chapter 5, Estimating Quantities and Qualities of Fecal Sludge at Community to Citywide Scales, in the IWA publication, Methods of Fecal Sludge Analysis, and provide some examples of how it can be used. This is Lake Malawi. If I asked you how many fish were in this lake, how would you estimate that? Even more complicated, what if I asked you how many of each species there were? It is difficult to estimate since fish are all underwater and you can't see them. And this is an analogy for the problem facing us in quantifying and characterizing fecal sludge from the community to citywide scale. Fecal sludge is stored underground, typically without records of what is there or how it is managed. But like the fish, we can develop methods to make reasonable estimations. And why are these predictions important? We need reasonable estimates of fecal sludge loadings in order to adequately design infrastructure and management solutions. Cities are rapidly growing, so you need to plan for total growth. But in addition, adaptive management plans are necessary that take into account the complex and dynamic situation as it changes over time. Without standard approaches, one result is that fecal sludge treatment plants are typically designed and built way under or over capacity, with negative impacts on public and environmental health and financial resources. So based on our field experience and research, we knew there must be a better way. And both quantities and qualities of fecal sludge are highly variable, and all of these management practices influence this, from type of containment, contents, storage duration, emptying practices, level of on-site treatment, quality of construction, groundwater, and temperature. So let's first consider quantification. It is important to realize that volumes of excreta produced per capita per day are not equal to what actually accumulates in on-site containments or what will be delivered to treatment facilities. And represented here are steps in the service chain. Number one is excreta production. Number two is fecal sludge production, which is everything going into the containment, such as excreta, flush water, cleansing materials, kitchen waste, or rubbish. Number three is fecal sludge accumulation, the results of production minus biological degradation and outflows. Number four is fecal sludge emptied but not collected, which also includes septic tank effluent if it is discharged to the environment. Number five is fecal sludge collected but not delivered to treatment. And number six is fecal sludge collected, which is delivered to legal discharge and treatment. And actual in situ rates of fecal sludge accumulation are the most difficult to estimate, but the most important for long-term planning of citywide sanitation. So how can we measure these underground volumes of accumulated fecal sludge? For individual containments, one way could be to measure volumes emptied by vacuum trucks or the VOLaser measuring device, which has been developed by the Muse group, and then divide by the time since last emptied. And more information on the methods can be found on our webpage and also in the sampling chapter. But then we still need a way to make citywide projections because rates of accumulation are highly variable and there are not standard per capita values for fecal sludge accumulation, which is the topic of the book chapter. For example, this graph from the book chapter is a summary of some values of accumulation rates reported in the literature. So let's next consider qualities. Say you are designing a planned treatment facility and so need to predict characteristics of fecal sludge that will arrive at the facility. In addition to the different management practices which influence the variability of fecal sludge at the level of individual containments, it is emptied and collected batchwise. What I mean by this is if the top figure represents a centralized sewer-based system, the wastewater from individual houses that is transported through the sewer is relatively homogenized during transport, and hence it is easier to predict and model what arrives at treatment. In comparison, if the bottom schematic is fecal sludge, it is much more variable at the level of individual containment, and this level of variability is delivered to treatment as it is not homogenized during transport. So what we need is a way to average out the complexity seen at the individual containment level, to zoom out to be able to make a weighted average so we know what needs to be managed at community to citywide scales. And one problem with making predictions is that qualities of fecal sludge typically do not follow a normal distribution, and so average and standard deviations alone do not provide adequate representative summary statistics. The figure on the left compares influent at the Lubiji treatment plant in Kampala, Uganda, of wastewater in blue and fecal sludge in red. And the figure on the right compares values reported in the literature for wastewater in red and fecal sludge all other colors. You can see the distribution of reported characteristics is much different for wastewater and fecal sludge, which also holds for quantities. And a common mistake is assuming a normal distribution, but the problem with this assumption is, for example, with an average value of 10 and a standard deviation of 25, about a third of randomly sampled values would have negative values. And this is clearly not meaningful for concentrations of constituents in fecal sludge, such as total solids, volatile solids, or COD. Taking an example of what this means from the literature, 108 fecal sludge samples taken in Ouagadougou, Burkina Faso, had a reported mean value of 9,014 milligrams TSS per liter, with a standard deviation of 8,480. If these results followed a normal distribution, it would mean that the probability of a random sample having a negative value would be 14.4%. That means that a statistical model would predict that about 15 out of 100 samples will have negative TSS values. And clearly it's not logical to report the data and try to make projections in this way. So different summary statistics are needed. So we have these diverse volumes and characteristics. How can we use them to make reasonable projections? If we just make a citywide average, we know it will not be meaningful, as explained by the assumptions of averages being based on a normal distribution. So the question we asked is, can we use statistics to find categories of data that predict or separate out different ranges of characteristics and accumulation rates in order to average out this complexity and make reasonable projections? For example, what if fecal sludge from households always had a higher total solids? Or if septic tanks always had a lower total solids? Or if public toilets also had higher ammonia concentrations? And that is the crux of our approach. Based on our experience, quantities and qualities of fecal sludge can be grouped by categories of demographic, environmental, and technical data. This example is from Kampala, Uganda, where we separated results from 180 on-site containments and separated them statistically by the types of demographic, environmental, and technical data written here. So correlation is not causation. Income level is not a cause of why characteristics might be different, but there could be a correlation due to things like quality of construction or flows of wastewater going into containment, such as only toilets or also with showers and kitchens. And we see here that total solids concentrations for containment type and income level were statistically significantly different based on these notches around the median. We can then use the total number of pit latrines and septic tanks in a whole community or city and/or the number of people at each of the income levels to make projections. The SPA part of SPADAT refers to spatially analyzable, meaning that these types of data can be mapped and used to make projections about characteristics and quantities of fecal sludge, for example, in different neighborhoods of a city. So what are the notches around the median? To account for the non-normal distribution of data, we use the confidence interval around the median, not the mean. In this way, we can separate out categories of data to use when making weighted averages. For example, high and low income level, or septic tank and pit latrine. And this figure illustrates the equation for calculating the confidence interval around the median. That is what the notches on the box plots in the previous slide are showing. The example shown here is for a symmetrical distribution of data, but you can refer to the previous slide and see that it also works for asymmetrical distributions. So we then use these values to make a weighted average for the city versus a global average. An example of applying this approach is if the accumulation rates for a city served by septic tanks and VIP dry latrines were 25 liters per capita a year and 190 liters per capita a year, with 1 million people using pit latrines and 100,000 people using septic tanks, just taking a simple average of the two accumulation rates would yield 107 liters per capita a year. Whereas taking the weighted average for the entire city would yield 40 liters per capita a year. Quite different values. In contrast, if a transfer station was being designed for an area within the same city, estimated to serve 500 residents with VIPs and 1,000 with septic tanks, the weighted average would be 135, a value 3.4 times greater than using the citywide value. For another example, you can refer to this calculation in the book chapter. Also in the book chapter is this case study from Lusaka, an example of how to design a sampling plan. This case study from the book chapter presents a case study from Hanoi and Kampala, where we evaluated whether a modeling approach could be valid within a whole city and also across two different cities. This case study was from Sursila, India, with an analysis of 180 on-site containments, demonstrating the difficulties we are still facing in standardizing field measurements and the impact on results, whether settled sludge or total sludge volumes are measured, or in situ or truck methods are used. Further examples on our website and in the book chapter about how data collected in this fashion could be used to reduce costs of characterization campaigns such as relations seen between different characteristics, or our Sludge Snap app, which is being developed to predict characteristics based on photos taken with a smartphone. If you want to experiment yourself with these types of data analysis, please see our open access data for more examples. At these links are data from 850 on-site containments from 6 different cities in Africa and Asia, with more open access data coming soon. Please contact us if you have any questions.
So that was a lot of information presented by Linda, but it shows very nicely how important it is to be able to sample properly, to analyze properly, and also how big the consequences are if you cannot do this correctly, because you amplify the results on a much bigger scale. So it's very important also when you start at the end that you go back to the beginning, how to do this sampling very efficiently and think about your sampling strategy properly, because it has a big effect. Later on, you will also be able to see the slides, and feel free to use as many pictures and as many information as you can, but please also refer to it appropriately, so they can also trace back that it comes from the ALX scientist, and we'll also be able to ask the questions to the right people if you want to search for more information. So the next slides will be from me about chapter number 4. And this chapter talks mainly about how you can set up experimental methods, how you can set up experiments for different purposes. What I really like about the books and the one that goes in front of this book is that they integrate so nicely. As I just mentioned, it's important to combine the different types of knowledge. So what you could see also nicely in this build-up of the presentations before, you saw Tamrat showing how to do proper sampling. And that's really about the status quo, to know what is present that is important to treat. Then from the previous book, from the systems methods on fecal sludge management, you can really learn where to treat it and how to treat it. So those are the nice additions from that part. And then this book you can use in how to do the analysis, how to do the sampling, how to do an estimation about the quantities and the qualities of your sludge. And then with this particular chapter, you can improve any kind of treatment methods, or you can do some experiments about which technology could be suitable for your specific stream of fecal sludge and your specific location. So what is in, can we have the previous slide? Yeah. Because what I like to show you here is that these are 2 top researchers. BJ graduated last week from her PhD in Switzerland, and she's pursuing other lines now, but she's a fresh PhD and she has a fantastic research delivered. So feel free to read that, use it, and learn a lot about how to prepare your fecal sludge in order to dewater it much better. And the next picture is from Santiago Septien, who is also one of the main co-authors of this book, and he shares a lot of his research findings in this particular chapter. So much credit to these good researchers. So now next, yeah, perfect. So how this chapter is organized, what it tries to show you is that there are different types of scales of experimental methods. So you start at the lab scale, which goes from milliliters up to liters. And you take a very small research question and you see, okay, what range do I need to maybe add my chemicals, or maybe how many temperature differences should I apply? So first, to get a bit of a feeling for how your fecal sludge reacts to different kind of stimulants. Then the next scale, if you think, okay, I feel quite certain with this findings in my lab scale, you want to see how it's doing in real life conditions. So you are able to move it up to the pilot scale. There's a very nice picture here also from the book, showing you a pilot scale on the facility. And what that offers you is real life conditions. So you have the variety of the fecal sludge coming in, you have the weather conditions, you know how it is to actually work there in the field in the same conditions. And you are able to also take a little bit more into account any kind of viscosity issues, pumping issues, how to get it from one tank to the next. So you already have a feeling for how things are going to react in a bigger scale. And once you're ready with your experiments in this scale, then you're ready to try it out in full. And a full scale, of course, is not so suitable for any kind of novel experimenting, but it is very suitable to see what you can change on a bigger scale if you're quite certain of a certain improvement. What this chapter presents very nicely is the 10-step approach. How do you get from something that you're wondering about in the field to actually finding a solution for your problem or finding a nice improvement? And the chapter takes you through these 10 steps. Now, the first one that is a very important one is to get a research idea. And typically that's something that hits you in an unexpected place. When you're biking home, when you're doing the laundry, and you think, hey, actually, what I was wondering, how could this and this be the case? And why is it not in a better shape? Or could this be related to this characteristic? So this is a very important one. But then once you have this idea, how to get that tested is to make a specific research question. So how do you cut down all the side issues and really get down to a research question? It's a very difficult step. All you master students, PhD students, you know how difficult it is to narrow it down to one specific research question. But once you have that, what you want to do is select the variable to measure. So which parameters are of interest for your research question? What you have then is to identify the design factors and to see in which ranges am I going to test this. If you are interested in a temper change, you're not going to do it from 0 to 100. That doesn't make any sense because you need to apply it later on to a full scale. So you want to narrow it down to the range that makes sense for you when you start to apply it in a full scale. Now, which factors could possibly influence your experiment? That's a very important one because you want to rule out any kind of influences. For example, if you want to work on microplastics, you know that you have to work with glass materials. And if you want to see which other factors are of influence, either take them into your experiments or make them the same for all your experiments. It's a very tricky one, but very important. Then what you need to do is go to the back of this book and identify the lab methods and the SOPs that are applicable for your type of research. Now, this book is very comprehensive already, but it's a beginning. And what we aim to do is to get all the methods that are constantly in development, to have a database that gives you the latest insights of all this information. What another important part is to determine the number of replicates. Now, that's also a tricky one because you want to be as thorough as possible, but you also know that any experiment and all these methods, they cost money and time and chemicals. So also to keep in mind that you don't want to make more pollution than you had in the first place. So all these factors play a role in how can you get relevant data out of your experiments. Now, the QA/QC protocol is a very nice one described also in this chapter. So make very good use of this. See the nice examples of how this is being done in previous researches. And then you're ready to perform your experiments. So how to set it up, work with your colleagues in the lab, and also enjoy the work, because this is a very important step of what you're doing here. Interpreting the results, now that can be a very tricky one. So did you really take into account, go back to the beginning, did you really identify all the influencing factors? And you have to be very objective here and test it also out on your colleagues. Like, I'm thinking that these are the results and this is how I interpret it in the findings. Would you agree with my line of thinking, or do you see also some factors that could play another role? So make sure you get a lot of interaction on this part. And then what you want to do is define what are your conclusions and recommendations. Are you ready for the next scale, or do you need to reject your hypothesis from the beginning? Was it not the factor that you had in mind that was really of influence? So there you're ready to really make an impact. And then the last step, share your findings, because we are all working in a field that is very much in development. I find it very encouraging to see so many people here in the chat already from all sorts of backgrounds and locations globally. This will also be shared on the other side of the ocean. So find each other and share your findings so we can all learn from each other and together bring the field a lot further. What are the further learnings if you really dive into this chapter number 4? So this is a kind of a guideline how to set up your experiments, and woven into this chapter are some findings about very specific topics in the fecal sludge management. There's one on the conditioning, how to improve the dewatering, and the other part provided by Santiago is really about drying for resource recovery. And that focuses on thermal drying and on microwave drying. So these aspects are nicely shown. So you learn also about the findings, but also about how did they set up their research facilities. I showed you again here these 4 main purposes why we do fecal sludge management and fecal sludge treatment. So the stabilization, nutrient management, pathogen inactivation, and the dewatering drying. So these topics fit very nicely, and it's important when you do your experiments that you also see, do I cover one of these fields? Do I cover maybe more? This is important to be able to link your findings to what the rest of the researchers are doing. Okay, now that's what I wanted to share with you today about chapter number 4. Make sure you give it a nice read because it's a lot of interesting information, and especially when you're ready to do some experimental work, it also gives you some encouragement that you started a small idea which can grow out into a real treatment plan. So be brave and get ready. Now with this, I'd like to give the floor to the modeling, because that's an aspect we haven't touched yet. We have seen some questions about this in the chat already. And modeling gives you a nice opportunity to be able to get some idea about findings without having to go into the laboratory. But it does give you a need for very good data. So, Damian, take us into your computer, please.
Thank you, Mariska. So this is a chapter which is a little bit different than other chapters in the book. The other chapters in the book are very practical, and they are, based on hands-on experience of many people, and it helps readers also to apply what is in these chapters also directly into practice. We also decided then to have a little bit, let's say, a challenging chapter in terms of the focus and in terms of the applicability at this moment, and it's a conceptual chapter. It is about citywide inclusive sanitation modeling and how a fecal sludge and non-sewered sanitation fits into that concept of integrated modeling. This chapter was written by my colleagues and myself, Carlos Lopez Vasquez and Francisco Rubio Rincon, and I would like to share the learning objectives. So, as we know, when you talk about citywide inclusive sanitation, we also need to include sewered and non-sewered areas. When we talk about sewered areas, which means centralized treatment plants, sewer systems, and recipients as well, we talk about research that started in 2 centuries ago, where we have more than 110 years of experience researching different systems, activity sludge system, biofilm systems for treatment of wastewater and sewage, while on fecal sludge and septic sludge management, our experience is not so long. So when we talk about modeling, the modeling of sewer system started really seriously in 80s, where in 90s it was kind of a peak of interest in that. So we have 30, 40 years experience in modeling of sewer system, but zero or little experience in modeling non-sewer sanitation and different technologies related to off-site treatment. So the purpose of this chapter is to bring these two fields together and to learn from the experience from the colleagues and from the modelers of sewered systems, and to see how we can translate that knowledge and transfer that knowledge into non-sewered area and make interfaces between, so that two fields are better connected and basically end up into one bigger integrated system, which is the idea of citywide inclusive sanitation at the first place. So these are the learning objectives. And can you click a little bit just to see if, oh, there is one part of the slide which is missing, which is very interesting. On the top, you should see the screenshot from 1991. Yeah, that is now there. The screenshot from 1991 that I made when I came to IAG for the first time. We operated at that time with the DOS systems. Internet was not existing. Can you imagine that? Mobile phones were not existing, and we were still modeling at that time sewer systems. And of course, when you click, I think that was just the time where the first internet shots were appearing, and it couldn't find wastewater or wastewater model at all. I clicked today, this morning, on that, and I got this screenshot, 79, 78 million matches. So it just shows the tremendous progress that we have done in this field. So on the next slide, I just introduced you to some quick literature on wastewater side. The most common literature which is used is on activated sludge models, ASM1, ASM2, ASM3, and so on and so on. That's for activated sludge modeling. And for anaerobic digestion modeling, the most common model is ADM, anaerobic digestion model number 1. In the current practice, these models are integrated into, as we call it, plant-wide modeling of the wastewater treatment plants. But now the trends at the moment are to integrate models of sewer systems, wastewater treatment plants, and recipients, be seawater reservoirs, rivers, and so on. So we have models very well developed, and here we just showed two other references, the most recent one on how to apply the models, and also many applications from practice. So when we talk about sewered system modeling, we can say that we are very far. The models are ready, the models are tested, the models are reliable, and we have lots of confidence into them, and many people are using them. So you don't have to be a modeler to use the models. You can be a user with a good knowledge of processes and treatment of wastewater, and you can nicely and easily use this. Many of our students are doing their thesis on that, and within a couple of months, they are ready to do really serious research jobs. So when we talk about the content of these models, it's quite complex. The more processes you are adding, the more requirements on the model you are adding, the models are becoming more and more complex. So what you need to understand is actually that the model is a representation of the reality, and you don't apply all models for all purposes. So there are different models that you apply for different applications and different goals. And this is just one of an example of very complex model, which include carbon removal, nitrogen removal, and phosphorus removal. The more processes you are in engaging, the more complex the model becomes. Next slide, please. So the easiest way to represent the model is in form of matrix. The matrix is very useful, and it gives an overview. And this is just the most simple representation of a matrix, including several processes on the left-hand side and materials which are involved in the processes. And here we talk about stoichiometry and kinetics of processes, and these are all necessary to have a good wastewater model. Please, next slide. But then when you talk about real modeling, then this comes at, so this matrix represents the slide just before, which includes carbon, nitrogen, phosphorus removal. So in order to model, you really need to understand the processes and to understand how this matrix works. And it takes some time. So don't get scared. You can also do that. So please, next slide. This is an example of a treatment plant in St. Martin that we also use in our sanitary engineering program. This is just a nice wastewater treatment plant. And when you go to next slide, you will see the process. Next slide, please. The process flow diagram. This is a normal. And then on the next slide, you can see how this process flow diagram is transferred into a modeling environment. We have a simulators which contain models, and this is a BioWin simulator, which is representing this little treatment plant that I just showed you. So now we are very happy with ourselves and with everybody in the sewered part of the city-wide inclusive sanitation. That's really going on, and you have more and more developments and even more accurate academic models and integrated models, plant-wide models. We model now incredible things. But I must say that one part we still don't model correctly in a sewered part sanitation, or not correctly, but maybe not sufficiently. The sewered sanitation is focused really on carbon, nitrogen, phosphorus removal, and even the removal of advanced compounds, micropollutants, and so on, but not on pathogen removal. And this is about environmental protection, but sanitation is about pathogen removal at the first place. And that is a chance where I see where the non-sewered sanitation modeling can really take a lead, so that sewered modelers can learn from the non-sewered people and vice versa. So let's start now talking about non-sewered sanitation. Why we should do modeling of non-sewered sanitation. But first, we get really, by application of models, we learn to be systematic, we learn to be also fundamental, but also practical and organized. So the practical understanding is very important. Then we also use all the chapters that we described previously, because for good modeling, we need good data, good characterization, because without that, the results of the models will not be good. So the modeling has no meaning if you don't feed it with good data. The fundamental understanding of processes is also missing largely in non-sewered sanitation side. While, for example, nitrification is the most researched process on sewered sanitation, more than 110 years of research there, we still struggle to describe properly complex chemical, biochemical, biological, and physical processes taking place in different stages of sanitation service provision chain. And then also the modeling will initiate community of practice, where we will communicate between ourselves, but also between other people involved in citywide inclusive sanitation. This slide is from the book, and basically on the left-hand side, you see the protocol for modeling, and this protocol is taken from the wastewater treatment modeling and applied in a non-sewered sanitation modeling. That was done by the purpose, because we want to apply a similar approach so that the interface and methodology is the same, but we deal with different material here. We deal here with the fresh or old feces and urine, with septic sludge, which have characteristics which are different than a wastewater, often mixed with the rainwater. So these are the main things that you need to differentiate when you work with non-sewered sanitation modeling. So the objectives are to really understand the accumulation of solids in the system, to understand how we can minimize sludge volumes in the containments, how we can enhance inactivation or even removal of pathogens in on-site sanitation systems, how can we predict sludge characteristics, and how can we work in a context of recycling and circular economy by using end products like biogas, nutrients, and so on. So when we go to the first step, you need really to formulate the objectives. The objectives will indicate which type of models you need to use. So you really have to be clear from the beginning. Why do you do modeling? What is the purpose of it? And what do I want to get out of it? Once you know that, you can continue. But don't continue without answering that first question. In this particular case, in the book, we did not cover all type of on-site sanitation systems. We started with the, let's say, 3 most common use technologies like toilet and containment, portable toilets, single pit latrines, and septic tanks. So for these 3, we moved into a process description, and it was really important to understand what is happening in these systems. Once we understand what is happening, then we can also describe what is happening. So, and that's what we need to describe, is described by the means of mathematical equations, in which we take into account physical, chemical, and biochemical transformations, both in terms of time and space. Once the processes are described well, we need to collect the data and verify. So for that, we use all knowledge that we have collected before. So we have to, in other chapters, what I mean before. So we need to determine the volumes of fecal sludge, also including urine. We need to determine characteristics of fecal sludge and urine. We can also say, and septic sludge. And what is important, we have these zones in some of these technologies, and we have to define what is the depth of the zone, what is the size of the zone, because these zones seems to be interconnected. One zone has impact on the zone before and after. And to assess the conversion processes, that's the core of the understanding of the systems. And of course, we need to estimate infiltration, percolation in the system, taking into account different type of containments. In the next step, I will just show you very quickly the proposed model structure for 3 different technologies. For a portable toilet, you see that these different zones are modeled differently. In this case, we have 3 zones, and there's connections between these 3 zones, and processes are happening, and we are describing them. If we go to this is for portable toilet, where the fecal sludge and urine is contained. When it's not contained, like in, for example, unaligned pit latrine, then we have more complex situation where the zones are interconnected, but also the zones are the content of the pit latrine is subject to interference with the infiltration and exfiltration. That has also to be taken into account. Only by taking all these aspects together, we will be able to get a good prediction of the model. And the last one is on the septic tanks, and you see if we have a septic tank with the 2 compartments, which is relatively common type of septic tanks, the most simple one. You see that the life becomes even more complicated, where we have to make a connection between zones in different containments, but also connection between containments. And if the tanks are made permeable, then you also have to take into account of infiltration and exfiltration. So these are proposed suggested concepts that can further be developed and to build proper models for these 3 containments. After that, we go into characterization of flows. So for that, we need to characterize fecal sludge and to fractionate that sludge. Characterization means characterization in terms of quantitative and qualitative characteristics. The book talks about both. In the chapter that Linda presented, we talk about Q&Q methods and other methods to quantify qualities. And in the other chapters, we talk about fractionation of the sludge and specific characteristics of sludge. But we should not forget inhibition and toxicity, because here we are talking about biological processes as well, and also chemical processes. These processes are in fact influenced by different parameters like pH in a tank, or presence of volatile fatty acids, or ammonia, or other environmental and other factors, which are a temperature as well, present in the system. And this can inhibit or toxify our biological population in the containments, and influence the results of the model. And also, pathogen inactivation is not included in the modeling of sewer systems, and we included pathogen inactivation in this chapter as well, and several methods for modeling of pathogens. So moving from there, so assuming that we can apply such a concept on an offsite sanitation systems, we come up with the approach where we look into life cycle analysis. This is the most appropriate look or approach to modeling, when we look into the full life cycle of certain technology, starting from a system choice, or through design, operation, optimization, improving, and upgrades. And at each of these different stages, you need to apply different models. At the beginning, the complexity of the models is low, but the impact on the technology choice is huge. So when you really want to save money, you do it really at the beginning. When you really want to upgrade or optimize your treatment and to do more academic research, it's towards the end. So but moving towards the end, the models become more complex and savings are less. So the maybe surprising message to you is, once you need to use the models, you can save the most money using very simple models at the beginning of your life cycle of your technology. Now, how that fits into a bigger picture. So once we do modeling on a micro scale, so we model individual toilets, we model septic tanks, we model latrines and other technologies that we also in the chapter propose how to model other technologies, but we did not give a conceptual solutions for that. Because for many of these already modeling has been done to a certain stage. So we need to put that together and to move from micro scale to a macro scale, from the level of individual units to areas in a city, that we could use this data and to agglomerate this data, extract what we need to model large scale areas, and to apply another level of modeling, which would deal with the selected information coming from the microscale models. So there we need to build interface between microscale and macroscale to get to this macroscale. So to get the data that we are getting from non-sewered sanitation, including fecal sludge management, to the same level as so that this, let's say, sector speaks the same language as the models coming from the sewered areas. And then we can put them together. So on one hand, we have quantification of the flows and wastewater in the sewered area. On the other hand, we have quantification of the flows and fecal sludge and septic sludge on non-sewered area, and then we can put it together. And then it would lead us to many exciting developments. And I will just mention one that we just developed in the time of COVID. It was developed by IG and the Institute for Water Recycling, KWR, for Water Research, KWR in the Netherlands. We developed a concept called DEMOS, which is a digital epidemic observatory and management system, which is really working on a citywide inclusive sanitation level, taking information on COVID from the sewer networks. And probably you have read a big deal of literature which came out in the last 2 years on sampling of sewage network and modeling of COVID in sewage network. So these are type of things that we easily can get from sewered areas. But this is also opportunity for non-sewered sanitation to provide similar information based on samples taken from the toilets, transfer stations, and fecal or septic sludge treatment plants. Put that all together, it goes to the cloud. Artificial intelligence, it does it work, and then we get recommendations to organizations who are dealing with the health in the area, like ministries, Red Cross, and others who are also, this can be also considered as kind of emergency sanitation. So this is how these models can be used, given that there is infrastructure which can provide particular data on particular compounds that are of interest in citywide inclusive sanitation. So what is the future? If we want to really go to true citywide inclusive sanitation modeling, we need to learn and to take knowledge from the sewered systems. We need to develop non-sewered sanitation models. We need, if we talk really about citywide inclusive sanitation, it's not only about technical models, it's also about other models, sanitation models, including financial models, but also social models. When we put that all together in the future, that we will call really citywide inclusive sanitation model. And we need to combine these models, we need to provide these interfaces, and we need to simplify it so that the complex models can run in the backgrounds and the users can see only the shell and get whatever the user wants to get from it. So the future of that is that it will not be a privilege only of academic people doing the modeling. It will be done by lots of professional people who will do that. And what I expect that there will be also business opportunities, that there will be companies doing modeling as vendors for us, and we can ask them to do studies for us, so that not all of us have to be modelers to be able to deal with the modeling as a tool for a modern champions in developing and implementing sanitation. So we do lots of efforts to put these outputs into our curriculum of Global Sanitation Graduate School, and I'm happy to see that many of these elements are part of master programs which are currently running at 42 universities in Sub-Saharan Africa, South Asia, and Latin America. And I also hope that students who are listening to this are also inspired by our talk of today, and will push their supervisors to provide them topics on modeling, on Q&Q, on experimental methods, on characterization, and laboratory methods as a part of your master thesis. And I'm looking forward to read your thesis and your results obtained using the book and knowledge from Global Partnership of Laboratories for Fecal Sludge Analysis. Thank you.
Wonderful. A lot of information, nice history class, and how to apply all these different parts of the research of the book together, and really do your get some benefits out of this. So this concludes our presentations. This was a review of the book, a short summary with nice graphs, with nice messages. And we've seen already some quite interesting questions passing by. I've seen one on power failure. I think it's 41. There was one on power failure and how to deal with sampling when you have a power failure happening. 41. Have you ever experienced power failure during storage and preservation of your samples? Well, that's a very important one, of course, because you see, we need to keep it cool. You could even freeze it. But what do you do when you suddenly suffer from power storage? Tamara, do you have any suggestions how you could potentially deal with these issues?
Yeah, yeah, this is not a very good circumstance that you have the power failures during the storage. But of course, your refrigerators can help a bit if it's not too long after failures. If it is just 2 hours or not more than 6 hours, it should be okay that your sample is still usable. But if it is one day, 1 week after failures, you cannot recover the powers for your refrigerators. That I don't think it is possible to use it again, especially for the fecal sludge having many of those organisms that change the properties, the qualities of your sample. So I would not suggest to use after 6 hours or after the power failures.
Very nice. Okay, so some suggestions how to deal with this. Maybe also spread your samples over different locations. That might also help.
I have power generator,
Yeah.
a reserve one.
A backup, indeed.
Yeah.
The next one that gives a nice question to you, Tamarat. What is the recommended sampling strategy when you don't have any emptying trucks yet, but you are planning a treatment? So how should you there proceed in getting the right data for your estimation of the quantity and the quality?
Yeah, of course, this is quite a challenging situation that if you have no emptying truck or emptying equipments for the on-site for the septic tank whatsoever that you have in the area. But my recommendation would be that before you conduct the sludge samplings, you need to understand or to review or conduct a kind of few observations that how many, what are the size and how many of those on-site systems you have. Then if there are variables, for example, that it could be septic tank, it could be cesspool, it could be uh, pit latrines, different in your desired area. So I think you need to find out that what are the most or the predominant systems that having in your areas. Then you can suggest that okay, if the most numbers are septic tanks, for example, then if we can collect the fecal sludge from those systems, it could be representative of your area. But of course, it very much depends on your budget. I think one of the big constraints for the sampling strategy is that, of course, the higher the better, the more numbers, the better to define the sample size. But our research budget could be not so many, except in the IT Delft, they may have much more budget. But in our institution in the south, we have the limited budget, so that it would be very much recommended to define properly first that what should be and where should be the proper areas that can represent the most. Like if the area having 80% using the septic tank, similar size, then it would be easier. But if you have so many varieties of those on-site system, at least you should have taken one of each system, and then you can at least get us proper samples before you can decide the treatment facilities.
Nice addition. And you could also think about starting in the back end. For which kind of plant would you have space, and therefore which kind of fecal sludge could you allow in your treatment facility? That could also be a nice interaction. There was also another question about, yeah, exactly. The agent-based modeling. Damien, would you like to take on this question? How can we model qualities and quantity parameters in agent-based modeling?
Yeah, I would not complicate it more than it's complicated already. So I wouldn't use. I would recommend to use the practices that are developed on sewered side, and to continue with that, and to copy the approaches on non-sewered side sanitation. So as long as quantity and quantities are modeled, we don't need to apply agent-based modeling. Where we can do it in a way that we have done it on wastewater side, and as it is recommended in a Q&Q chapter for quantities. For qualities, we have recommended in the chapter 6 the way to go as we think we could go. Of course, there are different ways to deal with that, but I would not start many different ways at the moment where our knowledge is still limited. And I would stick to the proposal that we have now put in a book, and where agent-based modeling could have much more sense to be applied is when we start really working on integrated citywide inclusive sanitation model, where we start including social and financial aspects, especially when we start talking about social aspects. There, I think there are things which are difficult to describe with the mathematical equations that we do for characterization, and then agent-based modeling is much more applicable at that stage. So the integrated model is not just one model. It will be a combination of different models that will be modular. It will be combined together. They will communicate between themselves through interface that we will define, and the communication they will be connected in a meaningful ways, so that only meaningful information are connected with each other, so that once you use the total model, you can get information that the model is constructed for or built for. So that's how I see it, and you will be able also to connect or to disconnect different modules into that integrated model, and to focus on your objectives. Depending on your objective, you will get different parts of the modules engaged, and not run unnecessary other modules which you don't need for your objectives. So that will be the structure of this future model as I see it at the moment.
So Erik, we hope this answers your questions. And another nice one was, is it always a linear progression from lab scale to full scale? I don't think so. In my opinion, you can switch between the different levels. You could also put in a demo scale in between. Typically, what I see happening working now at the utility is you have a full-scale problem or a full-scale challenge, or the legislation changes and you need to do other things. And then what you start to do is go back to the lab and think, okay, what is the case in my situation? I have this kind of fecal sludge, I have this kind of a product that I need to work on. And then you start to test out in your laboratory, what are my options and which parameter has the best effect on what I need to achieve on a full scale. So in my opinion, it's an iterative process. You go from full scale back to lab, back to pilot, and it's particularly the really novel ideas that you also need the pilot scale. And otherwise, you could go from full scale to lab scale and back to full. So it's definitely not always linear progression, but you need to be able to work out completely novel ideas and to be able to fix solutions or fix new regulations.
There are many parameters which are dependent on the scale.
Exactly.
Some fundamentals will not change in many cases, but for example, energy requirement of the technology, the data that you get on a lab scale, a pilot scale, and full scale is not linear. You get the benefits of the scaling for some parameters when you go to large scale plants. So that should be clear that different scales have a different objectives in the trajectory of moving from the invention to innovation. So I agree with you, Mariska.
Yes, definitely. And Mariska already touched in the presentation of her chapter. It's important to do the small scale experiments, not that they're the representation of the large scale, but this is easier to help us move in the right direction of the design parameters. So in small scale experiments, it's much easier to do the repeatability until we get to a point where we are ready to move to the larger scale. So that's why it's important to do it.
Okay. And next one, I think, yeah, the normal distributions. How about non-normal distribution models making predictions? Another one from Erik, who is interested in modeling. That's a good development.
But this is really the question for the part of the let's say the teams who are really dealing with statistics. Different distributions again have a different applications. If you find out that your normal distribution describes your data the best, then there's no reason to go to other types of complexities. But that depends on your particular, let's say, database. And there are statistical packages that you can check your data on and see which distribution fits your data the best. So the normal distribution is most commonly used, but for really let's say a proper answer to your question, when you have a particular case, I would forward you to the literature, the book of Marcos von Sperling, which is open access and was published 2 or 3 years ago, and I think it's entitled Wastewater Data and Treatment Plant Design. And in this book, you have really, very systematically described all steps with the dealing with the data, how you apply different methodologies, and what are advantages and disadvantages, with very nice examples. It's mostly focused on wastewater treatment, but the basic principles should be common also for non-sewered sanitation.
Nice addition. Okay. Is there standard minimum number of replicates that must be carried out for an experiment to be considered? I don't think so. It completely depends on how variable your matrix is, and also if you do a first run to see if you have triplicates, do you have a lot of variability in there? And if that is the case, you might want to go back to your design table and think again about how to set up your experiments. But if you find a nice constant result, then you could stick to what you've designed first. Tamara, do you have any view on this? If there's a minimum number, also for sampling, for example, how would you increase variability there?
Well, the more the better, for sure. But of course, the budget would be another questions that should we do that. But at least we have 3 replicates from the views points that the sampling also have a certain challenge that we may get the oily scum or the sediments which without our knowledge. So somehow we may need to get the good numbers of the samples. That's why the sample size design is quite important. And the other thing is that instead of having more replicates, I would suggest more composite samples. That could be better to ensure that we will get the representative of the characteristics of the Faecal sludge. So depends on the objective, depends on the condition as well, that is not required or the minimum numbers, at least 2 or 3, but the more the better for sure, but composite sample can help reduce the replications, I think.
Nice.
Yeah.
Okay. I would also like to ask a few questions a bit to the general, let's say, representation of the book. I was really wondering, we have now the FSM methods, we have the experimental designs. What are the next steps? What is going to happen in the field of fecal sludge management? What are we going to do with the book? How it will evolve from here?
So who would you want to ask, Tina?
Yes, I can start and maybe you can add. Yes, I mean, that's the first step. We wanted to have this published because we didn't have anything anything like that previously, aiming to start moving more towards standardized approach in the analysis of fecal sludge, which is quite an important aspect, because we saw that there are so many variabilities that we want to manage to contain. Of course, fecal sludge is going to be heterogeneous, but we have to make sure that we have the same uniform approach, then which would make it one step closer to the standardized approach. So then the next step is obviously, we need to look at the citywide inclusive approach. Damir already touched a little bit on the modeling part, but when we speak about analysis and when we speak about the way forward, we have to integrate both. We have the experimental methods, we have the methods for fecal sludge analysis. How can we combine and learn from each field in order to do this integrated planning and go for the next steps? How do we improve what situations we have at the moment, and how is this going to help us solve the challenges that we are facing at the moment?
Yeah. What I would like to see on connecting to Tina, what she said, is first that the book is used as much as possible, that it becomes a standard book for examination of fecal sludge samples and septic sludge samples. I am happy to see that the book is inspiring other publications which go even deeper in the practical implementation of methodologies and sampling and laboratory standards and so on. Certification is coming also along. What is missing is some verification of some methods that we propose here, because this book is a consensus of the opinions of different laboratories. 11 laboratories were involved in writing or reviewing specifically chapter 8 with the all methods there. So some of them are more established than the others. So we would like to bring these less established methods to a method that are accepted as such and globally used with maybe regional modifications which are needed. So that's the first thing I think we need to test what we have written there. Second is to collect the information. We still don't have a proper database with the fecal sludge and septic sludge data. We are planning to establish this global database where all published results will be deposited. The new results will be also uploaded, and we would like to develop a certain structure of that database so that the data can be accessed easily by students, practitioners, and everybody who is involved in the field in a very, let's say, practical form, web-based form. So we will be working on that. And we are also hoping that once we have sufficient amount of data, that we can apply some artificial intelligence, some trending and predictions for situations where we don't have all data from the sample analyzed. So with some critical basic analysis, how can we upgrade the picture of our sample without really taking samples or measuring certain parts of the sample? So that will be another step. And the third step towards real buying in of the book and work is to make video recordings of all the methods in the book to next to the book, so it will make a package so that you have the all information available. And we are busy with that already, and hopefully next year we will have all the analysis in the book supported by video materials. And then we come to the point of capacity building in the sector. That's important because at this moment we do not have sufficient numbers of labs. We have 12 labs which are kind of not certified, but which are have experience in staff and analytical equipment and history in doing fecal sludge samples. We would like to expand this base with many more labs who can be trained, and that they also upgrade their laboratory facilities to the level that they can become partners and start feeding their results into the database. So it's a 3-4 step approach that we need to do, and this we are at the beginning now, and I hope that we will get there. So actually I'm sure we will get there, but I want to get fast to that point, and for that we need to secure some additional support in terms of funding to implement our ambitious plan.
Wonderful, and get really the whole field to be mobilized and informed.
Yeah. We really need structured approach, synchronized approach, and that's what we do now with this. We established the basis for that. We have excellent partners, knowledgeable partners, but I think we are just at the beginning of the process.
Thank you. Nice words. We are at the time, huh? It's 11. Yes. So this material will be available for reviewing. You can see again all the chapters. Feel free to reach out and share the information and continue to discuss in this nice setting of the Global Sanitation Network. Thank you very much for all the attention, for the nice talks and the nice questions, and hope to see you again.
Thank you very much.
Thank you.
Thank you very much. I am going to post the link to the book to be downloaded on the group chat just after we complete it. Thank you. Have a nice day.
Bye-bye.
Bye.
Bye.